So in this video, I'm going to use the alternating series test when possible. So we want to determine if the conditions of the alternating series test are met, as well as convergence. So I'm going to do these two examples here. Okay, so I will remind you what the alternating series test is as we get into this. Okay, so for this first example, so this is an alternating series really because I've got the -1 with this exponent here. So that tells me this is very clearly alternating. So, okay, for this, there are three conditions that we need to make sure are met for the alternating series test. So we're told that this alternating series converges if the following hold. So all of the non-part of the alternating terms are positive. And if these are eventually non-increasing, and then if this goes to zero, if the series goes to zero. So, So this is what I'm focusing on right here. So, okay. Certainly these are all going to be positive. The next thing to kind of notice here is that, so if I were to just take the limit as n approaches infinity of n squared plus 5 over n squared plus 4. So if I divide everything by n squared, so let's see, actually I'll note this over here. So I'm going to take all of this and I'm going to divide everything by the largest power in the denominator. So this becomes 1 plus 5 over n squared, and then this becomes 1 plus 4 over n squared. So these two parts here are going to go to 0. So this limit is just going to equal 1. And so that's actually what this third condition means. So this needs to go to 0. Maybe I should state that as n goes to infinity. So the sequence does not go to 0, it goes to 1. And so this violates then the conditions of the alternating series test. Additionally, this is also the nth test for divergence, which says that a series diverges if this a sub n fails to, the limit as n approaches infinity of this series either fails to exist or is different from 0. So we've kind of killed two birds with one stone. This doesn't meet the conditions of the alternating series test. Also, it diverges by the nth term test for divergence. So this diverges for sure. Okay, so now let's take up the next example. Okay, so for sure these terms are going to be positive because I'm plugging in 1, 2, 3. Everything here is going to be positive as I'm taking the natural log, so no problem there. The next thing is, let's just maybe this quicker, so we'll go ahead and do the limit as n approaches infinity of the natural log of 1 plus 1 over n. So when I evaluate that, this ends up going to 0. So this will just equal the natural log of 1, which equals 0. So just to remind you, so that was one of the things that we needed. We need this part of the series to go to 0, so we're good there. So I think the harder part of this is proving that the series is definitely non-increasing. You need to back that up, so I'll make some space. Okay, so to prove whether this is non-increasing or decreasing is I am going to set my function, so natural log of 1 plus 1 over x. So the easiest way to do this is to take the derivative, so our old pal derivatives. So to find the derivative in this case, I've got to use the chain rule, right? So this is going to be 1 over the inside function, and then the derivative of the inside function. So just as a reminder, this right here, this can be rewritten as x to the -1. So when I take the derivative of the entire inside, the derivative of 1 is 0, and then the derivative of this is going to be -1 to the -2nd. So let's clean this up a little bit. So this now becomes -1 over x squared times 1 plus 1 over x. So this will equal -1 over x squared plus x, right? So we do want to just simplify that a little bit and take a moment to clean up the algebra. I guess I could even take this one step farther. I could rewrite this as, I could just factor out an x now and rewrite this like this. That would work. That might help with the next part of this. So I want to know, so for this to be non-increasing, I want to know when is this less than 0. And so, okay, let's clear a little space. Okay, so the thing about this function is that when I plug in positive x's, this whole thing will be less than 0, right? Because I have the negative up here. And in the context of the series, right, our series goes from n equals 1 to infinity. So we're only plugging in positive values into this function. So this is less than 0 when x is greater than 0 for sure. So what that means then is that our, so this is really always decreasing or non-increasing in this series. Okay, so we're all good then on the 3 things that we need for the alternating series test. And it says if these 3 things are met, then the series converges. So it's a little bit of work to kind of get there, but now I know that this definitely converges, and so I'm good to go. So I will leave it at that, and I will catch you guys in the next video. Thanks for watching.